Dr. Stewart, I'd like to thank you for coming here to tell us a bit about this project. I was wondering if you could just introduce yourself to us.
Sure, I'm a geotechnical engineer, Syracuse University graduate, almost 40 years ago. Glad that somebody's interested in some of the work that we've done. We're happy to share it with you. I hope it helps somebody.
All right, thank you. Could you give us a little history or a brief history or overview of the project at the Kirkpatrick Street Pump Station?
Yeah, let me tell you a little bit about what a pump station is, just for good background. As you know, sewers flow downhill, and when you get into areas of the city where the ground's relatively flat, the sewers either have to get fairly deep or you have to put in some kind of a pump to boost them. The way these particular pump stations work is that the sewage flows into a deep hole in the ground. A pump is set in that hole, and then the fluid is boosted and then flows down by gravity to the Metropolitan Sewage Treatment Plant. It's part of the Onondaga Lake cleanup that was started perhaps 30 years ago. The plan included upgrading several sewage conveyances and taking sewage from outfalls that would flow into Onondaga Creek during storm events and piping it directly to the to the sewage treatment plant. To that end, they needed to install a number of pump stations. This was one of several pump stations that were added around the county.
Okay. Was there anything really unique about this pump station that, as you said, there are many other pump station projects, but something unique about this that set it apart from all the others?
The pump station itself probably is sort of a plain vanilla pump station. It's a hole in the ground with a pump in it. It was added to an existing pump station, so they were building in close proximity to an existing structure. In fact, this was an addition, so they were building right next to an existing pump station.
Okay, could you give us a general idea of what soils underlaid the pump station? How did that affect the site exploration and construction?
It's a very interesting question, and let me start by telling you that it's in an area of Syracuse that has some difficult subsurface conditions. There had been a previous pump station constructed there, actually twice. The original pump station in the 30s and a later addition to the pump station in the 70s. We don't know much about what happened in the 1930s. We do know that there were some construction problems associated with dewatering in the 1970s. We were hired by the contractor who needed help getting the project constructed in the early 2000s. We did not participate in the initial subsurface exploration. The work was done for a government agency, and they did not have a clear record of what the previous construction was. I am not sure why, but I suspect it had something to do with the construction claims and the way that the original job might not have gone so well. But we got involved on behalf of the contractor to try to figure out how to build the pump station addition.
Okay.
The subsurface investigation that had been done at that time consisted of a single test boring, conventional sample boring done by ASTM D 1586 and 1587. They had encountered sand and gravels to about a 40-foot or 50-foot depth. The depth of the pump station addition was about 35 feet. So it required construction deeper than 35 feet for that purpose. That's what we knew when we got started.
Okay.
Shortly after we got started, we found out that there were some drawings and some records from the previous construction. There were some deeper test borings. They were valuable. All the subsurface information indicated that there was a fairly deep deposit of sand and gravel, relatively porous, permeable sand and gravel. This pump station addition was also to be constructed right next to Onondaga Creek, where the stage was set for a relatively high water table, close to an almost unlimited supply of water in the form of Onondaga Creek, very porous soils. Right off the bat, we became concerned about how we could control the water so we could dig below the existing pump station to put this addition on. I could frame that a little bit for you. I'm sure almost everybody's gone to the beach.
Mm-hmm.
If you go to the beach, you know you can dig a hole down to about the water table. Below the water table, you can't make any progress at all. The soil comes in as fast as you bail it out.
Right.
And
Mhm.
we anticipated a very similar condition for the pump station.
Okay. In terms of dewatering the site, what combination of field tests, laboratory testing, and calculations were done to determine the ranges of value for permeability, but also for the flow of water coming into the site during construction?
Initially, dewatering estimates they're important because they affect the cost of the construction. You need to put in a number of wells to lower the water table. You need to size your pumps to pump an appropriate amount of water out of the ground to pull the water down. All that translates to cost, so contractors or project managers would be very interested in how much energy is required to pull the water down, how many drill holes would be required to pull the water down. Dewatering on a project like this could easily exceed $100,000 in cost, so it's not an incidental cost. The initial estimates were based basically on the grain size of the soil.
Okay.
So based on the standard penetration test split spoon samples that would come back from a conventional test boring, engineer would look at that and say, well, this is sandy gravel or silty sand, and I go to a textbook and say, well, the coefficient of permeability is probably somewhere between 1 times 10 to the minus fourth and 1 times 10 to the minus sixth. Now they sound like fairly precise estimates, but 1 times 10 to the minus fourth is 100 times the value of 1 times 10 to the minus sixth. So it's actually a fairly wide range. That means when you run through and do a calculation that you might be lucky to be within an order of magnitude or 2 orders of magnitude, maybe between 10 and 1,000 gallons per minute or between 100 and 10,000 gallons per minute of pumping. So our first step was to evaluate or estimate the permeability of the soil. Now, the soil varies. It's laid down in individual layers. The most permeable layers exert a much more dominant influence on how much water would come into a well or need to be pumped down to depressurize a stratum. And some of those dominant layers may be relatively thin and almost indetectable with the conventional soils exploration. So laboratory permeability testing has not been found to be particularly valuable for lots of construction dewatering projects, just because you could be off by a fair amount and they need more precise estimates. Nevertheless, the conventional tool for estimating the dewatering volume would be a solution of a differential equation called the Laplace equation. It's a seepage equation. You want to take a quick look at this diagram. Here it shows water flowing into an excavation. This just happens to be the pump station excavation, but you can see water's coming in from a nearby creek, water's coming in from the surrounding ground, water may be coming in from below. The Laplace equation gives us a mathematical method for solving that equation of flow. Based on the boundary conditions, we can determine how much water would be coming into excavation, and then we could size the pumps accordingly, figure out how to get the water out of it.
Okay.
I should tell you about field testing, though.
All right.
Certainly the most reliable method of determining how much water you're going to have to pump is to actually go through it, do it, and start pumping the water. That's really the most reliable method, of course, and that's telling you how much you have after the fact. But building a big hole in the ground and bringing in different size pumps and putting in various numbers of wells is very expensive. So we try to come up with a better order of magnitude in advance. The best method, short of building a total excavation or a full-scale excavation, would be to put in some wells and do some pump tests. And you would put in a deep well, put some pumps in it, and just pump as much as you can and measure the volume and how the rate diminishes with time. As you pump water out of the ground, you'll get less and less with time, but eventually you may reach a steady state condition. That steady state condition would be related to the grain size of the soil, as well as all these minor geologic details that could really dominate the problem. So it's a very good test.
Mm-hmm. So how did you approach the dewatering design for this project?
Well, the first step was to make an estimate of the permeability based on the visual and manual examination of the soils. We were able to do some grain size analyses and refine those estimates a little bit. But really the next step was to go through and do the analyses like we showed on the previous diagram, solve the Laplace equation. Turns out that there's a very convenient and ages-old method for solving the Laplace equation graphically, and that's by constructing a flow net. And I know that your fellow students will have a lot of experience doing that, and CIE 337 is one of the rites of passages for geotechnical engineers. It's kind of a frustrating experience, but it's a very useful tool. It's not used as much anymore because we have computer methods that basically solve the Laplace equation numerically now. You don't have to do the graphical solution, but the graphical solution gives you a very simple and intuitive grasp of what happens in the problem, and it's very good. And I think it would be a big mistake to totally avoid doing flow nets anymore. It's just like doing a free body diagram for a mechanics problem. It's just very valuable, and it helps you build intuition as to how seepage problems work. So our second step was to do the analysis using flow nets, because we didn't have computers in those days. Third step was to then size a dewatering system for the flow that we felt might be coming in through the analysis of the flow net. One of the big problems with doing a flow net or doing the numerical solution of the Laplace equation is defining the boundary conditions. And if you go back to the diagram that we showed a few minutes ago, you can see that the boundaries are not particular. Well, the boundaries here are well defined in terms of Onondaga Creek and the flow toward the pump station, but the boundary condition from the left-hand side of the page and the boundary condition from down below are essentially intractable. It's not easy to establish just what those would be. So we basically had no choice but to go out and do a field test. And the field test was to install a well, a pumping well. Actually, we installed 2 pumping wells, and we installed several monitor wells nearby. From those, we could establish some pretty good boundary conditions, at least in terms of where the flow was going and how far away certain monitor points were. We installed a well, put a big pump in the bottom, and pumped the water like crazy, came up with basically a real-life solution to the Laplace equation, and then we went back through and back-figured what the coefficient of permeability would be, and used that to plug into the geometry of the full-scale excavation, and we were able to determine the dewatering load, how big our pumps would have to be, how deep the wells would have to be, and how much money it ultimately was going to cost our contractor friend to do the work.
So were there any challenges or unforeseen things that affected the project?
I think one of the most unforeseen aspects that nobody could have foreseen, or nobody did foresee, was the fact that the groundwater at depth was highly saline. In fact, it was 4 to 5 times saltier than seawater. That in itself isn't that much of a problem. It's not uncommon to have saline groundwater in some areas of the country. The saline groundwater in Syracuse was a little bit of a problem, and the fact that there was so much of it to be removed became quite a concern. And it became a concern because of the Onondaga Lake cleanup effort. It turns out that some of the sediments on the bottom of Onondaga Lake were relatively immobile sediments, but in the presence of salt water or elevated salt content in the water, that those chemicals became more mobile and more apt to leach out of the sediments into the lake, where it became a very significant concern. During the pump test that we ran, the folks studying Onondaga Lake raised an alarm that the chloride contents from their tests had spiked, and they jumped up quite significantly, and that was probably because during the pump test we were disposing of thousands of gallons a minute of salt brine into Onondaga Creek, which flowed into the lake and showed up on their sensors. Somebody talked to somebody who talked to somebody who talked to somebody who found out that there was a pumping test going on, and some environmental engineers put their heads together and decided, we can't allow this. We can't allow you to dewater at that rate. So that changed the whole complexion of the project considerably. And the question to me was, how do we dig such a deep hole below the water table in such permeable soils and not pump a lot of water into the lake? So kind of between a rock and a hard spot. It was a very interesting engineering challenge to deal with. And it's the subject of the paper that we put together on it, to try to document that for people, because it was interesting, but because it had significant local importance.
All right. So I want to thank you for coming in and sharing this project with us. Is there any last words you want to say to the students before we leave?
Wish them good luck. I hope the next 40 years is as beneficial to you as the last 40 years have been to me. I certainly look back with fondness at my Syracuse University education, and hope you guys will look back fondly as well. So good luck to you.